Hello guys. Let's talk about topic 12. Let's try to do those three problems. Pretty good summary of the whole process done here. If you look at pages 415 and 416, but especially 415, that's what I've emphasized the most. 12.1, page 415, the summary, work in thermodynamic processes. The work done on an ideal gas at a constant pressure, work is equal to negative P times delta V. The work done on the gas is positive if the gas is compressed, and delta V is negative, and negative if the gas expands, dV is positive. So the gas itself might do positive work, but they regard it as negative as far as like what the environment does. It's work done, the environment does negative work, but the environment does positive work if it compresses the gas. So work equals negative P delta V. The first law of thermodynamics, according to the first law of thermodynamics, when a system undergoes a change from one state to another, the change in its internal energy, delta U, is given by Q plus W. So if you do work on a gas, positive work on a gas, for example, if you do work on it by compressing it, you have changed its internal energy. The internal energy has changed. And if you heat it up somehow, some other way, you add Q to it, you also increase the internal energy. So different books write different things, and it can get pretty confusing. What they call negative, what they, what their regard, how they regard a negative value, how they regard a positive value. So let me just summarize this. Let's look at it for our purposes at least, and we'll kind of take it from there. So they tell us if you're going to compress a gas, the delta V is negative. So the work that's done on the gas is negative P times delta V. Well, what does that mean? Negative P times delta V means if the change in the volume is a reduction in the volume, delta V is a negative number. Negative times negative is a positive answer. So if you compress a gas, you did work on the gas, and that's positive work. If the gas expands and does work on the environment, so to speak, delta V is a bigger number. Delta V is a positive number. Positive times negative is a negative answer. So the work that was done on the gas is negative. The gas actually loses internal energy by doing that work to bring it outward. This can be a little confusing, guys. The big takeaway is P delta V. Depends what book you're looking at. P delta V is kind of what rules the day. Which one's negative, which one's positive. Some books, will switch the whole thing upside down. And they'll call, I just don't even want to get in there. I mean, that could probably mess you up more than it's going to help you. But they do switch this up and reverse what they call what. The big takeaway is P delta V. If delta V is a reduction in volume from what it was before is a negative delta V. Negative delta V times negative P is a positive answer. You have increased the internal energy. You've increased the internal energy of the gas when you have compressed it. You have done work on the gas, a positive amount of work on the gas when you compress it. If the gas expands, it does work. But for our purposes, on the gas itself, the gas had negative work done on it because it lost energy. And its internal energy went down. So maybe that's a way to look at it. Look at that page. Look at the book in general, you guys. We got to do that. Page 415 and kind of take it on from there. The change in the internal energy. The change in the internal energy of a gas, or of an environment, I guess you could say in general, but the change in the internal energy is heat plus the work done on it. Now, if the work's negative work, it lost internal energy. This delta U is the internal energy of the system, and that's what they're talking about here. Again, other books switch this around. They go Q minus W. Why? Because they define that differently. We're not doing that. I like the way this book does it. This book does this pretty good. There's a couple things I don't like about what this book does, but in general, they do some pretty spectacular things, I think. Certainly better than I could ever do, writing a book like that. So they do great. Delta U equals Q plus W. We look at something like this. They talk about different sorts of processes, you guys. You can look at a process they call, an isobaric process. An isobaric process, an adiabatic process. All right, we don't need to say process, we already know it's process. Adiabatic, isovolumetric, isovolumetric, and isothermal. All right, there's some processes for you guys. Christian, this doesn't, it shows up okay, right? It's decent? Okay. Pretty decent, okay. So you got isobaric, adiabatic, isovolumetric, isothermal. What's going on with this? Well, for an isobaric process, from the Greek word varos, means weight. Isobaric process means equal pressure, constant pressure process. Let's just read it down the line. Let's go down the line here, guys. I'll read it, you guys look at it. Isobaric process is one that occurs at constant pressure. The work done on the system in such a process is negative P delta V, whereas the thermal energy transferred by heat is given by Q equals NCP delta T. So they got it written there. I'd rather not write that down. I don't want to overwhelm you with some of this stuff, you guys. But we'll see it when we do some of the problems. So an isobaric process is one that occurs at constant pressure. The pressure does not change. The work done on the system in such a process is negative P times delta V, whereas the thermal energy transferred is given by another equation, Q equals N C sub P delta T. All right, with the molar specific heat capacity at constant pressure given by Cp equals Cv plus R. All right, in an adiabatic process, no energy, in an adiabatic process, no energy is transferred by heat between the system and its surroundings. Q equals 0. So no energy is transferred by heat between the system and its surroundings. Q equals 0. In this case, the first law, delta U gives you W. Delta U equals W, which means the internal energy changes solely as a consequence of work being done on the system. The pressure and volume in adiabatic processes are related by, they got something there that I'm not really going to talk about right now. But the big takeaway here, what do we got? Isobaric process, the process takes place at constant pressure. Adiabatic process means there is no heat transfer between the system and the surrounding environment. Nothing comes in from the surrounding environment and nothing leaves from the system in which everything is taking place. All change in internal energy that will take place is not going to be done as a result of heat going in or out. Heat is not leaving or coming in. Only the work that you do to something is going to change the internal energy for an adiabatic process. So Q, there is no Q transfer. Q equals 0 in an adiabatic process. Adiabatico, nothing is being transferred, is what it means. Greek word also. Isobaric, constant pressure. Isovolumetric speaks for itself, but let's say it anyway. In an isovolumetric process, the volume does not change and no work is done. For such processes, the first law gives delta U equals Q. There is no work done in an isovolumetric process, you guys, for our purposes. There's got to be a change in volume for work to take place. So it's kind of weird. I mean, with the adiabatic process, Q is 0, so delta U equals W. For an isovolumetric process, work is 0, so delta U equals Q. Kind of interesting. For an isothermal process, occurs at constant temperature. Iso and thermal, thermos, temperature can mean heat too, I guess, but it depends. I don't want to get too much of a language lesson here, guys, and a lot that I don't know. But when you hear the word iso, isa means equals, the same level as. Isothermal means the temperature is kept at the same temperature. An isothermal process occurs at constant temperature. The work done by an ideal gas on the environment is given by this. There's a good derivation of it. I wish we had time. We don't. So for an isothermal process, when they talk about the isothermal process, you guys, they're talking about, for such instance, the first law, the work done by an ideal gas in the environment is given by this. So this gets a little wacky. The work that you do on the environment, that means the work done on the gas is negative, but the work done in the environment is positive. It's a little wacky. N stays constant, R stays constant. We said that T stays constant. It's an isothermal exchange of what's going on. Times the natural logarithm of the ratio VF minus VI. So there it is. It's coming right from the and that's from the isothermal. It's too important not to talk about. So there it is, you guys. So we got it. We're gonna try to mess with this stuff and try to make some sense out of this, and let's see where it goes. Let's take it from there. Let me see. We're gonna do as much as we can. Christian is staying with me. Thank you very much. This guy's doing tremendous work right here, guys. You got to thank him for what he's doing, because I don't know. It's just remarkable. So that's good to see. So there it is. Okay, that's for the isothermal. Let's go. Let's do this thing. Let's just get it. Let's get it done. 1:14:21. Let me run you through it. You guys, again, all of this is solved for you. So we're not gonna, you're gonna get it. We're gonna make it. We're gonna figure it out. I'll see what my bosses say to me, how we got to approach stuff. But I think the way we're going is the way we're going. Okay, so problem number 1. Regarding this, topic 12, problem number 1. An ideal gas is enclosed in a cylinder with a movable piston on the top of it. The piston has a mass of 8 times 10 to the third grams. 8 times 10 to the third grams is 8,000 grams, guys. 8,000 grams is 8 kilograms. And an area of 5 square centimeters. That is 5 times 10 to the negative 4 square meters. And is free to slide up and down, keeping the pressure of the gas constant. How much work is done on the gas as the temperature of 0.20 moles of gas is raised from 2 degrees Celsius to 300 degrees Celsius? What does the sign of your answer to part A indicate? Well, the gas is going to expand. It's going to move the piston, and that's negative work done on the gas, but positive work done in the environment. So let's kind of look at it, get a feel how we actually did it. We said work was PV equals nRT. That gets us out of the woods a lot of times when we're doing this stuff. The pressure is constant. The volume will change. Divide by P on each side. that pretty legible from there? You can see it. You see it okay? Okay. Me up close, I can see the marks that are being made by my bandage here. But so I think, but as long as we're seeing it, we're good. Okay, V equals nRT over P. There's a VF and there's a VI, I guess, right? The VF will be nRTF if you're going to heat it up over P, or not heat it up. I mean, something else could happen too. You got that. The VI is nRT I over P. So we got those two things right there, guys. Looking pretty good. Tell you what, let's get down to the business of it. W is W. Negative P times delta V. Negative P. Well, then we say VF. We said constant pressure, so P is going to be the, N is the same, R is the same, P is the same. N ain't changing, R ain't changing, P ain't changing. Okay. Well, okay, if you want to do something here, I mean, take the P and distribute it, and the P's all cancel. The P's all cancel, the NR is the same, might as well just reverse distribute it out. It's called factorization, right? Come out to there. Here's the P. The P here, a P there. Can you see how it looks okay? Okay. Just want to make sure you see what I'm writing, guys. I've got it to here. Yeah, I mean, it looks pretty, that's actually pretty good. I think we're looking at. Okay, now, so we got that. W is equal to this. They are saying, let me see what they are saying. VF trying to figure out now what the heck just, let me think here. This looks okay. Oh yeah, I never put, I'm sorry, I should have left the N, I should have left the minus right here. The minus is there, so if you want, you can switch them around. It still works out. I don't want to get too nuts about that whole thing. Multiply by -1 across here, and everything just, it's all a horse apiece, guys, as long as you can get it right. So you've got this. W equals 0.2 moles times 8.21, 0.31 rather, I'm sorry. Got this. Well, we already said that. We already said how this works out. What does that mean? That's A. And I wrote it out here. You can read it in the notes. Read the notes. According to this bookkeeping scheme, the gas does positive work on the surroundings. Yeah, it does positive work on the surroundings, but it does, it experiences negative work in giving up that work that it's doing. So how does that say, how does that relate to what's going on here? So saying B, what does the sign of your answer to part A indicate? Does positive work on the environment, but what's being done is the environment, I can almost say is doing negative work on that. It's like it's losing all, it's doing all this work, but it's losing internal energy doing that. There's not work being done on it, there's negative work being done on it, but positive work on the environment. So that's the deal. That's one. 14. A cylinder of volume 0.300 meters cubed. See, forgive me here, guys. 1 second here. Yeah, we put everything in there that had to be put. Yeah, we're fine. An ideal gas is compressed. Okay, let me start over. I'm sorry. A cylinder of volume 0.300 cubic meters contains 10 moles of neon gas at 20 degrees Celsius. Assume neon behaves as an ideal gas. A, B, C, D, E, F, G, H, I, J. Yeah, I'm not lying to you. It's that many letters. All right, let's see what we can do. A, what is the pressure of the gas? B, find the internal energy of the gas. C, suppose the gas expands at constant pressure to a volume of 1 cubic meter. How much work is done on the gas? Negative work is done on the gas. Positive work on the environment. I'll tell you that right now. D, what is the temperature of the gas at the new volume? E, find the internal energy of the gas when its volume is that 1 cubic meter we talked about. F, compute the change in the internal energy during the expansion. Likely to lose internal energy when it does it. Compute delta U minus W, which will give you the Q. Must thermal energy be transferred to the gas during the constant pressure expansion or be taken away? During the constant pressure expansion, we'll talk about it. I, compute Q, the thermal energy transfer. J, what symbolic relationship between Q, delta U, and W suggested by the values obtained? Okay, this is quite a bit. You're looking at it, I can't keep rereading it, guys. You got it in front of you, you got the solutions as well. Let me run through it in the most logical manner that I can, and we'll see what we can say about it. Guys, 14 is a monster. You saw me read it. You heard me read it. So let's go for it. Part A, for the problem they got there. 14, a cylinder of volume 0.3 meters cubed contains 10 moles of neon gas at 20 degrees Celsius. Assume neon gas behaves in an ideal gas. A, what is the pressure of the gas? Find the internal energy of the gas for B. So A and B right now, let's just do. What is the pressure of the gas for A, and find the internal energy of the gas. So what we got here, sorry about that, guys. You got PV equals nRT. If you divide by V, you are done. Divide by V on each side. Plug in all the appropriate stuff. What is it? You're going to see it in my notes. 10 moles, 8.31. 20 degrees Celsius is 293 Kelvin. Volume in cubic meters, you've got to make it in cubic meters if it's not already given to you. They gave it to you, it's 0.3. So 10, 8.31, 293, because it's 273 plus 20, that gives you 273 Kelvin, and here it's 0.3. At the end of the day, guys, you'll see it in the work. There it is. B, what is the internal energy? Internal energy, U. They come up with this through consideration of the ideal gas law and what we know regarding transfer of momentum and what we know regarding kinetic energy. It's a long story. It's a beautiful proof they give. Pretty straightforward. What is it all about? nRT is the same as PV. It's pretty crazy. Those are in energy units as well. If you're careful about it. Well, what do you got? 3 halves is 3 halves. We already found the pressure, and we already know the volume. That's it. Multiply it all the way out. You multiply everything out, plug in all the appropriate values. And we got that for B. For C, suppose the gas expands at constant pressure to a volume from 0.3 cubic meters to 1 cubic meter. At constant pressure, it's expanding. Remember the P times delta V? The negative P times delta V? How much work is done on the gas? Negative work is done on the gas, positive work is done in the environment. D, what is the temperature of the gas at the new volume? Okay, let's just kind of look at that and take it. So that's that. C, W equals negative P delta V, negative the 81,116, the delta V, the final is 1, the initial is 0.3. Sounds good to me. We already delivered this speech. Negative 56,812.7. Absolutely. Work is done on the environment. This much work was done in the environment. If you take the negative out, that's how much work is done in the environment, done picking something up, but that's how much work was done on the gas. The gas lost. The gas, it basically gave the work went elsewhere, so that's going to manifest itself in a number of ways. They want to know what the temperature is. Again, you go to the bread and butter, guys. This should be okay. You should be okay with this. I'm not going to ask you too many crazy stuff. This is stuff you probably saw in high school, or you probably saw somewhere else in college. If you're seeing this for the first time, it shouldn't be that bad. We've already seen this quite a bit. It seems to be the bread and butter that gets us through a lot of stuff. This will work. You want to find the temperature? Go ahead. Divide by NR on each side. P is the 81,116. The volume, the new volume, it went from 0.3 cubic meters to 1 cubic meter. The 1 goes here. So 81,161 times 1 divided by the product, 10 times 8.31. It's that simple. What's going on here? Well, given the circumstances, there's the temperature, and that's D. So it started somewhere else. The temperature was higher though. The temperature had to be increased for this whole process to happen. So the temperature did rise for that all to happen. You can see it right there. E, what is the final amount? So the final U, now remember initially we had U, the initial environment with which we were dealing was here. We got this for an answer, and that's when we had T was something different, right? T was whatever it was, whatever we had it at the time. I think we had it, and then we raised from that, we had 20 degrees Celsius, 293, and we went about it. So that's the U, initial, so to speak. What's the UF? good to me. Three halves is 3 halves. N is 10. R is 8.31. TF, yeah, we said it was a lot. That's a lot. It's a lot more than we had earlier. So it makes sense that U is going to be a bigger number on this one at that point. So let's see what we got. When you do this, you got UF $121,745.655. Forgive all the mumbo jumbo, guys. That is J, joules. From 100, almost 122,000 joules. From here, about 37,000 joules. Yeah, it changed quite a bit, didn't it? What's the change? What about E? What's the change?
F.
F, right, I'm sorry. I'm enjoying this problem so much, I don't want to end it. You know, so we got F right here. You know, what are they saying for F? What's the delta U? UF minus UI. Well, there's UI. There's UF. Do the subtraction. Change in the internal energy, huh? Yeah, I mean, there's a lot that just happened. I mean, this thing didn't work on the environment. You know, work was done on the environment, so I already lost internal energy in that regard, but then it gained a net gain in internal energy total. I mean, kind of interesting how that all plays out. You could kind of say the change in the internal energy, just trying to look at this thing. Okay, it looks good. We'll talk a little bit more about it in a second, actually. That's F. G, what's going on here? What's the Q that happened, the whole thing here? So they're saying here, what kind of, was there a net, there had to be a net energy transfer, guys. There's no way this thing gained internal energy after it did work on the environment. There must have been a lot of heat added onto this thing. How much heat was added onto it? Man, my gut is telling me if the internal energy changed from here all the way to there, and you also did this amount of work on it, I mean, I don't know, I look at the change in the internal energy that occurred. So that went in as heat. Somewhere heat got in here, the change in the internal energy means that much heat went in addition to all the work that it did without losing while still gaining. I would add the positive counterpart of this guy. The opposite of this plus this will probably tell you the total heat that was in there. Is what my guess is saying, and yeah, indeed that is what's happening. Very important problem here, guys. Very, very, very important problem. That's why we're doing it. That's why it's 5 o'clock and we're still here. We got here, what, 8 o'clock? 8:30. So I mean, we're here for you guys. So I know everybody's gonna work hard, do well, okay? We got delta U Q plus W. What does that mean? Well, that means if you want to solve for Q, go ahead and do it. Subtract W on each side, you solve for Q. What does that mean? Well, okay, we just said delta U was this. There was a change in the internal energy, according to our bookkeeping. Yeah, there was a change in the internal energy minus the work. Minus the negative work, minus the work that this thing did on the environment. It did all this work on the environment, so it lost this work, it lost this capacity to do work. So even that had to be accounted for. Minus a minus is plus. Sure makes a lot of sense, guys. Q is plus 142, comma 035.9 joules. The work that it did on the environment had to come from somewhere. Somebody had to give them the capability to do that work. I know it says negative. Yeah, throw that out the window. It's negative work that it does. It's negative work that was done on it. It lost that work. It gave that work up to the environment. For it to give up that much work to the environment, minus a minus is a plus 56,812.7. That's how much heat was put in to help it do that work, in addition to helping it gain, delta U, change in internal energy. There was a positive change in internal energy, and it also did work on the environment. Account for it. There it is. Very important. H. What does this tell you? For H, I'm going to speak it to you guys. You read the notes. Thermal energy must be transferred to the gas. There's no way. This energy didn't come from anywhere, from nowhere. There had to be thermal energy put into this thing for the gas to do positive work to the environment, negative work to itself. The work I did, yeah, I lost that. He lost this much work. He lost this much capacity for work. Where did it go? To the environment. Okay, it's a positive amount of work it gave up. Minus a minus is positive, plus the change in internal energy. And it's right there. So for I think they said something. I'm not. Compute Q, the thermal energy transfer. We just did that. What's delta U minus W? Delta U minus W is Q. We already did it. Already done. Right here. Right here. J. I just love walking around this room, man. All right, so what symbolic relationship between Q, delta U, and W is suggested by the values obtained? Man, it sure looks like it. Look at it. I mean, we accidentally, we found this out. We found this out, whatever it is. It turned out that Q was the same thing as that. So what's suggested, that's what's suggested. You can write it like that, Q equals delta U minus W. Perhaps a little more straightforward is delta U equals Q plus W. Very, very significant problem. Very significant problem. Let's see what we got here, 21. And of course, 21 is 19 parts long also, so that's going to be fun. All right. Let's take a look at 21, you guys. So we'll do kind of the same, same kind of approach. Just hit it pretty hard and see what happens to it, okay? 21, an ideal gas is compressed from a volume of VI equals 5 liters to a volume of VF equals 3 liters. Again, a liter we said is 1,000th of a cubic meter. So 5 liters is 0.005 cubic meters. 3 liters is 0.003 cubic meters. So 5 liters is 0.005 cubic meters. 3 liters is 0.003 cubic meters. While in thermal contact with a heat reservoir at T equals 295 Kelvin, as in the figure. During the compression process, the piston moves. Okay, so you do this. with a heat reservoir, and the heat reservoir doesn't really change the temperature at all. During the compression process, the piston moves down a distance d equals 0.130 meters under the action of an average external force of 25 kilonewtons, 25,000 newtons. Find A, the work done on the gas. There is work done on the gas here, guys, because you're compressing the gas. The environment's doing work on the gas. Positive work is done on the gas, whereas when the gas expands, the gas does positive work on the environment. B, the change in the internal energy of the gas. It's going to get internal energy, more of it. C, the thermal energy exchange between the gas and the reservoir. We'll talk about that. D, if the gas is thermally insulated, so no thermal energy can be exchanged, what would happen to the temperature of the gas during the compression? If the gas is thermally insulated, so no thermal energy can be exchanged, what would happen to the temperature of the gas during the compression? It's going to be interesting. All right, let's take a look at it. Let's run through all those. All right, for 21, you guys, what's going on here? Same average force, the whole thing here. Let's figure out. There's going to be work done on the gas. So for 21A, work equals the average force times the distance through which you're moving it. The average force is 25,000 newtons, 25 kilonewtons. You're moving it a distance (3, 2, 50 joules). It's the work done on the gas. B, by virtue of contact with a heat reservoir, this is an isothermal process. So B, what's going on here? They said it's in contact with a heat reservoir, so the temperature ain't going to change. By virtue of contact with a heat reservoir, this is an isothermal process. And we are told that the internal energy of an ideal gas is a function of temperature alone. So delta U equals 0 because isothermal, no temperature change. So that's pretty beautiful stuff, guys. So read the notes. It's in the problem. I'll say it again. Pretty, again, very significant. Because it's in contact with, by virtue of contact with a heat reservoir, this is an isothermal process. Temperature is not changing because it's a heat reservoir that's in contact with it. And we are told that internal energy of an ideal gas is a function of temperature alone. High temperature, high internal energy. Low temperature, low internal energy. We are told, and I quote here, the people told us, the internal energy, we are told that the internal energy of an ideal gas, is a function of temperature alone. Delta U is 0 then, because isothermal, no temperature change. C is saying the thermal energy exchange between the gas and the reservoir. That's interesting. The reservoir stays constant temperature. So, C, again, read this one too. Ditto on this one, guys. The work done on the gas would increase the thermal energy of the system were it isolated. But here, since it is in contact with a thermal reservoir, it is isothermal because heat exchange occurs. So the work done on the gas, the work done on the gas would increase the thermal energy of the system. Simple as that, if it were isolated, but it's not. Since it is in contact with a thermal reservoir, it is isothermal because the temperature stays the same because heat exchange occurs. So there's heat going from the gas to the reservoir. It's being transferred there. So the temperature, so it's not doing anything to the temperature, you guys. The thermal energy exchange between the gas and the reservoir. Correct. So they made that remark. So if that's the case, what's happening here? The internal energy does not change. So whatever work went into it, all that work got converted to heat and went into the reservoir, you guys. So for this one, it's here. So remember when we say delta U equals Q plus, this is also important. Hugely important, just like the PV equals nRT. is very important. You guys have probably seen, like I said, different books write it differently. Every book I've seen writes this. This sometimes get written a little differently, okay? So watch out. But stuff like that is big to watch. Okay, let's go to this guy then. So you're saying for C. We said there's no change in the internal energy. What does that mean? Well, it means a lot. I mean, if this much work was done on the gas, guys, you would otherwise increase the internal energy. You would otherwise be increasing the internal energy of the system. In what regard? Well, I mean, you did work to it and it's there. Well, now that if there's no change in that, any Q, for that to happen, there's got to be this, whatever work you did, that amount of energy is going to go to the heat reservoir. It's going to increase the temperature and bam, get transferred right to that heat reservoir. So what does that mean? Exactly what you're looking at. Yeah, the reservoir might have it's probably got a lower temperature than what just happened. Okay, that is C. Crazy stuff. Important, very important. D, if the gas is thermally insulated, so no thermal energy could be exchanged, what would happen to the temperature of the gas during the compression? It's going to rise. It's going to rise. So you could look at it, see exactly how I want to say that. Now I got to be kind of careful here. It's absolutely going to rise, that's for sure. If the gas is thermally insulated, so no thermal energy could be exchanged, what would happen to the temperature of the gas during the compression? So there's no thermal energy exchanged. Delta U, there's a lot of stuff here, would increase. Delta U and ideal gas would increase, and delta U is proportional to T, so temperature would increase as well. I'm not exactly thrilled how they wrote this, but I also know they're very, very smart people, so I'm going to follow them. This we know. Okay, we said this, we got it. This is one of those benchmark statements that we know like we know our name. So if no heat were leaving and no heat were coming in, that's not to say it doesn't get hotter. You got to watch out for this, how they say that. Q is 0 means Q didn't leave and Q didn't go in. Well, what did happen then? Well, if that's 0, all of the work you did is going to go right to internal energy, is what it means. And, that stuff, and, they're both, delta U would be W, equal W, it's greater than 0. Delta U would be greater than 0 and would increase. Delta U of ideal gas would increase, and delta U is directly proportional to temperature, so temperature increases. For ideal gas, temperature increases. For delta U, delta U, didn't we say, is solely dependent on temperature, absolute temperature. If delta U is increasing, if there's a delta U that's positive, an increase in delta U means an increase in temperature. I smudged this. Can you see that? It's visible, okay? It's fine? Okay. That's it. Very, very important. Very important. I would have loved to have told you live, but this is the closest thing to live I can tell you, man. So you got it. You guys know how to do it. You know how to do it.